All right, we're about 2 minutes out. So I want to, thank everyone that's been able to attend. I mean, so what you're going to see this afternoon is the culmination of, really, 4 years of education at Louisiana Tech. Capstone, I don't really, there's very little that I teach in terms of new material. There's a lot of expectations, and the students have to, pretty much design, their whole system and everything. We started this back in winter quarter. I gave them an assignment to, create a whole system for a petroleum hydrocracking process that was about 50,000 barrels per day feed. And that was literally about the level of direction that they had. So they had to get into, do their own research into the literature, figure out how to accurately simulate that, work through a lot of those challenges. And then, this quarter we've been, probably focused more on the economics and sizing the plan and doing a lot of things. There's a lot of challenges with this particular system. There's a lot of the kinetics, the Thermo. It's a complicated process, and what you're going to see again is kind of the culmination as they apply all their various techniques and skills that they've learned in all the classes, kinetics, heat transfer, momentum, and everything into this design process. They've been working in groups of had a couple of teams of 4, had mainly groups of 3, a couple of people, a couple of groups 2, and then one person working by themselves. So kind of a variety of how many people are kind of working together and everything on that. So we're going to get started. We got a pretty quick kind of timeline that we've got to work through these. So you're going to see, like I said, the culmination of, a group's worth of work of, almost 6 months, and the last couple of months have been under this unusual kind of COVID experience and all. So they've got about 20-minute time slots. I've asked them to present in about 17 minutes. We'll have a few minutes per question and answer. I would ask the audience, if you've got questions, to go ahead and type them up in the chat box, and then I'll ask the question, so that we're not all just kind of stepping on each other and everything as we're going through the Q&A. So I would encourage people to go ahead and type questions and everything. And I may not be able to get all of the questions and all, but go ahead and type those up, and we'll work through them to the extent that we can. So with that, first group, I'd like to go ahead and introduce, Hannah, Mitchell, and Brandon to go ahead and go.
All right, I am going to share my screen. All right, does anyone have any issues seeing my screen?
We see it.
Awesome, great. Okay, let's get started then. So like Dr. Palmer just mentioned, my name is Hannah Lilly.
My name is Mitchell Porch.
My name is Brandon Stewart, and this is our catalytic hydrocracker simulation. In this simulation, we're taking 50,000 barrels per day of VGO from a vacuum distillation tower, and we're cracking it into gas, naphtha, kerosene, and diesel. Okay, so this is our net present value. So we use this equation to calculate our net present value of $955 million. This is based off of the fixed capital investment, cost of operating labor, waste treatment, utilities, raw materials, and revenue.
So now we're going to get into some of our process flow diagrams and equipment specifications. So taking a look at our overall PFD, we start with a VGO feed coming from a vacuum gas tower, like Brandon said. We pressurize that and heat that up to reactor conditions, and send that in along with a hydrogen feed that is coming from a steam methane reformer. We use reactions of hydrogenation and cracking to create our 4 cut fractions of diesel, kerosene, naphtha, and LPG. You can see here that our product stream of our reactor is being sent all the way to E107, where we're using heat integration. And this saves us money in both utilities and the fact that we do not have to use a heater in this case because this process stream is so hot and needed to be able to be heated up. Some other takeaways from this PFD is our topology. As you can see, we have 4 distillation columns as we separate the heavier components first, and as you go downstream, we separate the lighter components. Another type of topology that we attempted to use was a fractionator, which would have reduced the number of columns necessary, but unfortunately we were unable to get this to converge in ChemCAD. Another key takeaway here is the fact that we were unable to have a VGO recycle. So the reason why is because this took a negative effect on our kinetics. So instead, we're just selling that at a reduced price instead. Taking a look at our cost breakdown, you can see that our reactor is 94% of our total FCI. This is due to such a large calculated volume based on our volumetric flow rate of our feed and our chosen residence time. Another key factor to this price is our MOC, which is we decided to go with stainless steel because of the consideration of hydrogen embrittlement. You can see that our heaters go for 3% of our FCI, which we were able to reduce due to heat integration. Taking a look at our reactor section of our unit, we can see here that we have a mass balance that does seem to check out. We take a look at our reactor, R101, has a height of 170 feet and a diameter of 34 feet. Taking a look at our product stream of our reactor is being sent to E101, where it is reduced in temperature, which allows us for easier flash of hydrogen, where we're able to recycle this hydrogen and pressurize this back up using a compressor. We size the compressors based on this equation in the left, where we have an inlet and outlet pressure chosen with a volumetric flow rate and a K constant. Another key takeaway here is our heater, which allows us to heat up our VGO feed to reactor conditions. Taking a look at our first and second towers, we have a mass balance that also checks out. Our first 2 towers are very, very tall. As you can see, it's 300 and 220 feet. This is due to a very low tray efficiency that we calculated, and that's based on the light keys and heavy keys that we selected for these towers. Another key takeaway here is our heater. We were unable to use high pressure steam for the bottoms of this tower due to such a high temperature coming off. So instead we chose to use a heater. And at E104, you can see that we're taking the bottoms of T101 and sending that in as utilities as another form of heat integration, which saved us a lot of money. I think it was around $10 million for not having to use a heater. Taking a look at our last 2 towers, our heights are not as tall as the first 2, and this is due to easier separation of these lighter components. Another key takeaway here is what I mentioned first at our first overall PFD is E107, where we were able to save money in utilities in a form of heat integration.
Now we're going to take a look at our kinetic and our thermodynamic validations. So to validate our kinetics, we used a literature source that cracked VGO into 4 components, which were diesel, kerosene, naphtha, and gas, like Mitchell mentioned earlier. So we validated these kinetics at the 4 temperatures in these graphs below. And it's important to note that in the literature, the reactor was held at a pressure of 2200 PSI, so we also applied this to our reactor. After reactor optimization, we determined that the optimal temperature and residence time for our kinetics were at 824 degrees Fahrenheit and an LHSE of 0.9 hours, which is about 55 minutes. So in the table to the right, you can see each cut that we're making as well as the weight percent at our optimal conditions. It's important to note here that we're also including unconverted VGO as one of our cuts because not all of our VGO is being converted, and therefore we do need to consider VGO that's leaving. Like Mitchell mentioned earlier, we're not able to recycle our VGO due to the negative effect that it had on our kinetics. So that will be sold, which we'll discuss later. In order to validate our thermodynamics, we put a flash after our reactor and plotted the mole fraction of hydrogen leaving the top of that flash drum against literature data. So in the graph on the left, we can see the 8 thermodynamic models that we considered and compared those to literature. And then the graph on the right shows the 2 with the smallest sum squared error, which were SRK and VTPR. Though VTPR technically had the smallest sum squared error, due to the computational time associated with using VTPR thermodynamics, we moved forward with SRK. So the literature source here consisted of 11 different runs at various temperatures and pressures. And it's important to note that run 10 had the closest temperature and pressure to what we're actually running in our reactor. So it's important that SRK had a good fit at that point specifically, which it does.
So now we'll talk about the optimizations performed with our system. So our first optimization is the reactor optimization. The reactor optimization had the biggest impact on the net present value. So I can see from the graph on the left here, we analyzed the net present value in respect to the residence time as well as temperature. And the net present value actually decreased as we increased our residence time and decreased our temperature. So as you can see on the graph on the right, this is the optimization performed within the range that our kinetics were validated. So we had a net present value at 824 degrees Fahrenheit and 0.9 LHSV. And this is our tower pressure optimization for all towers. The net present value was analyzed with the tower pressure, and we had an optimum of 41 PSI. And here we have the tower optimizations where we analyze the net present value in respect to the number of trays as well as the feed tray ratio. So tower 101 had an optimal number of trays of 38 trays and a 0.3 feed tray ratio. And towers 103 and 104, we did the same thing with those. And we analyzed the net present value in respect to the number of trays. And tower 103 had an optimum of 12 trays and a feed tray ratio of 0.2. And towers 104 had a optimum number of trays of 16 trays and 0.4 feed tray ratio. And we did not optimize towers 102 due to the fact of lack of convergence. And as a result of the lack of net present value effect, we thought that we could just move forward with our simulation without optimizing that one.
Now we're going to take a quick look at the commodity pricing for our raw materials and our products. So here we have 4 graphs of the pricing for our 4 products: diesel, kerosene, naphtha, and gas, which is priced as LPG. So this data goes from January of 2000 until December of 2019 to show that the pricing is changing a lot over the past 20 years. Specifically for our simulation, we considered data from January of 2016 until December of 2019. These are the past 4 years of data, as well as we're a pretty good average of the pricing over the past 20 years. So these graphs show price per volume. So we have our products price per pound in the table on the left. And you can see that our gas is our most profitable per pound at 49 cents, with diesel not far behind it. We also costed VGO and our hydrogen similarly, looking at data from January of 2000 until December of 2019, but solely considering January of 2016 until December of 2019. It's important to note that our VGO graph looks a little bit different. So instead of month-to-month prices like we gathered for the other graphs, VGO is costed as number 4 fuel oil, which only had data on a year-to-year basis instead of a month-to-month. Our hydrogen is also costed based on methane prices. Like Mitchell mentioned earlier in our simulation, that we'll be sending methane into a steam methane reformer, which will create the hydrogen that we are using. These are also costed based on volumetric flow rate, or based on volume in the 2 graphs, and so our cost per pound are in the table above. So our total raw material costs are about $880 million, with most of this being comprised from the VGO. And that's due to the fact that we're sending in more VGO from the VGO to hydrogen ratio, and we're also able to recycle hydrogen while we aren't our VGO. We'll be making about $1.37 billion from our revenue of our products. So it's important to note here that we'll be selling our 4 products that we've mentioned earlier, as well as our unconverted VGO and the excess hydrogen that both weren't able to be recycled fully. So you can see here that diesel is our most profitable cut at 39% of our total revenue. We also completed a sensitivity study to show the NPV changing on a month-by-month basis. just to show that it really does matter which months that we're considering in our pricing, because we could easily have almost no revenue or double or triple the revenue based on the months that we considered with our commodity pricing. You can see that our optimal NPV is the red dotted line and is a pretty good average of this data.
Okay, so now we're focused on the process safety aspect of our simulation. So this is a PNID of our system. Some key takeaways from this PNID is that we have pressure relief valves on all vessels, reactors, and drums, as well as the discharge side of the positive displacement pumps and compressors. So for these components, we have relief valves for liquid services, safety valves for gas services, and safety relief valves for liquid and gas services. Now I want to direct your attention to the reactor. We have a rupture disc in series with a safety relief valve with a pressure indicator in between. The rupture disc actually protects the safety relief valve from any type of corrosion due to hydrogen embrittlement or any type of hydrocarbons that can get through. And the pressure indicator actually notifies the operators if the rupture disc has blown or if there are any pinhole leaks past the rupture disc. It also has taken an effect of a runaway reaction with the worst case scenario. So this equation here, we were able to calculate the explosion for pounds of TNT. So if we was to have a runaway reaction, the worst case would be equivalent to 440,000 pounds of TNT. So at 300 feet, the damage would probably be to probable total destruction of buildings. And at 3,300 feet, you will have destruction of steel or aluminum panels. Fastenings will fail as well as followed by buckling. And the standard housing panels will blow in as well.
So the last thing we're going to discuss is some process controls both for our reactor and our distillation towers. So as Brendan mentioned a minute ago, one of our biggest concerns with our safety is a runaway reaction occurring in our hydrocracker. So our reactor will have a cooling jacket on the outside with temperature indicators both on the cooling jacket and on the reactor. The temperature indicators on the reactor will have two different control loops that they'll be feeding into. The first will control the cooling jacket fluid and turn that on once we reach a temperature above 825 degrees Fahrenheit in the reactor. Our temperature indicators will also control the valve that is letting in process fluid into the reactor in order to cut that flow if we are approaching a runaway reaction. One other consideration that we have is a quenching system, which isn't pictured here, but will be a step between adding cooling fluid to the jacket and cutting our reactor feed. This quenching system would have a condenser on the hydrogen line and would cut our fuel sent to the VGO heater in order to send in cooler feed into the reactor. These are all three precautionary steps that we have in order to avoid runaway reactions. And if we do encounter a runaway reaction, we do have the pressure controls that Brendan mentioned a minute ago. As far as our distillation towers, we have some process controls that will be on all four of our towers. For the tops of our towers, we'll have level indicators both on the condenser and on the surge drum. This will just ensure that these aren't overfilled. On the bottoms of the tower, we'll have a temperature indicator on the bottoms leading into the reboiler, which will control the amount of utility fluid that will be entering the reboiler. This will ensure that we're sending in an appropriate temperature of our fluid back into the tower, which will help us maintain the purity of our tops and bottoms of the tower. That's all we have for you guys today. Dr. Palmer, how can we answer questions that folks have given you?
Yeah, so on the runaway, did you calculate how much energy removal, well, I guess backing up, how much potential energy, could be given off in a runaway, and how does that compare to the cooling capacity of the jacket? What would be the cooling capacity be of the quench?
Yes, sir. So I did some calculations, but the data that we were getting from KimCAD didn't seem accurate and didn't accurately reflect an exothermic reaction. So we weren't actually able to get that data like you're asking for.
On the hydrogen, what were you doing with the excess?
That wasn't able to be recycled. Sorry, I'm going back
How
to
much
it.
was recycled and what was done with, yeah, excess hydrogen?
We were
So,
able to, go ahead, Hannah.
no, go
Sorry.
ahead, Mitchell. You got it.
Okay, I was just stating that we were able to recycle about 43,000 pounds of hydrogen. That's how much was going through the loop. Because of the recycle convergence, I think we were only able to close off about 90% of that recycle loop. So that's why we were losing about 10,000 pounds.
So
But
what,
I think,
I mean, were you selling the 10,000 or what was happening to it?
yes,
Yeah,
sir.
we sold that 10,000. That was like the 1% of our revenue, which we sold at about 75% of the fresh feed cost of hydrogen.
They're asking, was there any purity requirement of the hydrogen?
Yeah, so sorry, our hydrogen was purified to 99.9 mole percent. We can ensure that we weren't flashing off our products into that recycle. So we have that, but I mean, realistically, we would actually have to treat the hydrogen that's leaving before we could sell it, which is why we had to downgrade in the price.
Gotcha. Is there any change that you would make to the system depending on, variation of your feedstock pricing or I guess product pricing?
I think depending on product prices, like if we had considered a different set of years, or if products change a lot in the future, we might consider running at a different temperature and time in our reactor to be able to make the most profitable product. So diesel was one of our most profitable, so we made a lot of diesel. But realistically, if gas were our most profitable, or kerosene or something like that, we would skew our temperature and LHSV in order to have that be what we're making the most of.
Was kerosene, did you assume that it was being sold as jet fuel?
Yes, sir.
Yeah, we're up against 120. So at this point, let's go ahead and thank our speakers. Good job, guys.
Thanks, y'all.
thank you.
All right, we got next up our next team. Let's see. So we got Christy, Parker, and Michael.
Everyone see that okay?
Yep.
Awesome. Just before we begin, I'd like to give a brief thank you to everyone being here, friends and family, as well as the industry professionals, and of course to the staff of Louisiana Tech for getting this all set up for us. Before we start talking about our presentation, my group mates and I would like to introduce ourselves. My name is Michael Voss.
Hi, I'm Christy Johnson.
Hey, I'm Parker Renault.
And this is our VGO hydrocracking model presentation. So just to get started, this is our table of contents. We're going to start with a process overview and base case, then moving on to some optimizations, as well as costing, reactions and components, our thermodynamic validation and kinetic validation, and finally some safety, and then we're going to open the floor to some questions. So to start, this is our process overview. As you can see, our process is broken down into 3 distinct sections, with section 1 being our feed, basically our hydrogen and hydrocarbon coming in, which comes into the reactor at a ratio of 20:1 hydrogen to hydrocarbon. Our reactor, which operates at 842 degrees Fahrenheit, 2,175 PSI, and has a residence time of approximately 40 minutes. Section 1 also contains our cross-flow exchanger between the reactor inlet and outlet, as well as our hydrogen recycle and gas purge. Moving on to section 2, we have our gaseous product and our naphtha product coming out of our first 2 separation towers. And then similarly in section 3, we have our second 2 towers, which separate out our kerosene and then heavier products such as diesel and our residual.
And this is a summary of our best case NPV that we arrive at after using the costing equations and everything from our Turton textbook. You can see that our final NPV came out to be $221 million. And the revenue was greater than the raw material costs and our capital investment in utilities. And this is just to break down our capital investment for you a little bit more. You can see that the reactor makes up a very large portion of our FCI, and that's mostly just due to the nature of the system, with the reactor being such a high pressure and temperature, and also containing an excess of hydrogen, which could lead to hydrogen embrittlement if we use cheaper materials of construction. And so the stainless steel was adding a little bit to the cost. And the rest of our FCI was made up of towers and trays, heat exchangers, and surge tanks. So now I'm going to go a little bit more into some of the optimizations that were completed on our system. The first and probably most important was the reactor optimization, because if we weren't operating at the correct space, time, and temperature, then we wouldn't be maximizing our profit from converting to our products. And so you can see from the graph here that we were able to find an optimum at a temperature of around 842 degrees Fahrenheit and a residence time of 0.67 hours, or around 40 minutes. And we would have liked to test higher temperatures to see if we could get that MPV up just a little bit more, but due to our limitations of our kinetic data, that was the highest temperature we were able to test. However, we would suspect that once you started to get the temperature too high, you would overcrack those valuable diesel and kerosene products into naphtha and gases, which are less valuable, and the revenue would begin to drop. And now on this slide, you can just see sort of that trade-off between space-time and reactor volume. Since the reactor did make up such a large portion of the FCI would increase greatly whenever you increase the residence time of the reactor by making it larger. So at those lower temperatures, you're not able to make a profit because the reactor cost is so expensive that it outweighs that revenue that you could be making at higher temperatures. And the next optimization that we performed on our system was on our towers. And so the first thing that we did was try to figure out what number of stages we needed to have for our towers and what the optimal feed tray location would be. So we tested 3 different feed tray locations, which was the bottom quarter of the tower, the top quarter of the tower, and the middle of the tower for all 4 of our towers. And on this slide, you can see the towers 1 and 2, you needed to have the feed tray in the middle. And then now you can see that for tower number 3, you still needed to have the feed somewhere in the middle, but for tower number 4, it actually needed to be a little bit higher up the tower. And this is just to summarize the impact of the tower optimization on our MPV. So run at a base case before some of the other optimizations. So this MPV shown is lower than our final MPV, but the beginning base case was around 68 million. And after optimizing the towers, we were able to get that up to 97 million. So that was about a $30 million impact on our MPV. And you can see the summary of the different number of stages and feed trays that we arrived at for each of our towers. Another thing that we optimized with our towers was the pressure. So due to time constraints, we weren't able to optimize the pressure of each tower individually, which would be another step in our process as we continue to move on with this. But we did optimize the pressure of the system overall, and found that our towers operated best at a vacuum of 10 psia, and this helped impact our MPV by around another $2 million. And also optimized the flash drum that we used to separate out the unreacted hydrogen after the reactor so that we could recycle that. So optimizing the flash drum, we were able to find that a pressure of around 3,000 psia and a temperature of 95 degrees Fahrenheit was the optimal conditions for that flash drum, and kept the hydrogen mostly pure, with mostly some propane did get leaked into the hydrogen, but we continue to monitor our kinetics, and that didn't seem to affect how our reactions were proceeding.
Yep, so now I'm going to start and talk a little bit about our process flow optimizations performed in our system. The primary one being this cross-flow exchanger set in section 1, which basically heats the feed coming into the reactor using the effluent of the reactor itself. So we're able to lower our heating costs and that save our MPV about $3 million in total.
We also performed a topology optimization. So at the beginning of this project, we also considered the fractionator configuration, in which you have a larger column that then separates out the cut fractions that are then further separated using daughter columns. However, this did pose many challenges for us, especially whenever it came to convergence and KimCAD, as well as the specifications that needed to be set on the fractionator. However, we were able to run preliminary economic runs on this configuration, and we saw that it did not yield an optimal like our traditional towers, just due to the little amount of flow that we were able to pull off from the side streams. We were able to do a pseudo optimization on the fractionator, in which we were able to graph a column profile, and we were able to see the concentration of each one of our cut fractions at different locations up the tower. And this would give us the optimal locations where we would want to place our side streams in order to maximize our our product yield. However, this would need to be continued to monitor as you continue to do optimizations, especially whenever you change the number of stages within the fractionator. And now Michael's going to talk about costing a little bit.
So now I'm going to start talking about our price validation for our raw materials and products. And as you can see here, this is an example of the technique that we use to model our pricing data out in the 14 years that our project would be running. You can see there's lots of different lines on this plot, and the black dots are the actual literature values, basically from EIA.gov, which is a government agency that reports energy costs. And you can see that black squiggly line is kind of just a general trend that's expected for the average number of values, as well as the green line is the actual average of those values over the next 14 years expected. And then the blue line is the previous 10-year average, basically from 2010 onward out to 2034, which is the entire scope of our project. This is then repeated for all of our components. As you can see here, this is an example for kerosene and our number 4 distillate, which is the same thing as our VGO feed and our residual. And then finally, we have our naphtha wholesale price. This was actually gained from tradingeconomics.com, so a slightly different website with a slightly different time scope. However, we were able to perform the same technique on modeling the prices out and able to obtain the same values. And then finally, at the bottom here, you can see our pricing table, and this includes all of our cut fractions as well as our hydrogen and VGO feeds with all of their 10-year average costs, some historic highs and lows, and finally a suggested price that we were able to use in our system. This is our component pricing sensitivity analysis. So for this, all this shows is essentially if the prices were sold for our components at a higher or lower price. And as you could see on those previous plots, the price varies quite dramatically over time, especially in such a volatile market as the one we're in now. It's important to perform sensitivity analysis. And as you can see here, if our products were sold essentially at their highest historic high, we would bump our NPV almost up to $2 billion, excuse me. However, if they were sold at a low price, it would reduce our NPV to negative $750 million.
We were also able to perform a theoretical profit margin to see if our system could not only be profitable, but also give us an indication as to where our optimal may lie. However, it needs to be noted that this only considers the revenue that we would gain from selling our cut fractions, as well as the raw material cost. It wouldn't consider the other things that go into our net present value, such as the FCI, utilities, and other operating costs. And these do track well with what our reactor optimization yielded. And now I'm going to talk a little bit about the feeding product component validation. So essentially, this is a fraction distilled graph from numerous sources, and we varied our components in order to try and get this distillation curve to line up with what literature provided. And we did have to sacrifice a little bit of accuracy and the sheer amount of components that would be in our feedstock in order to save on computation time. And as you can see on this slide, these are the 6 components that we ended up deciding on to represent our VGO feedstock. And they range from low molecular weight and boiling points all the way up to extremely heavy and high boiling point components. And these include straight chain paraffins, as well as cyclic compounds, as well as aromatics. And these are the reactions that we decided on. The first 10 reactions are our VGO feedstock going to our individual cut fractions. And then the latter reactions, 11 through 17, are the degradation reactions that we needed in order to best represent the curvature that you will see in our kinetics for diesel and kerosene at the higher temperatures. And as you can see in the leftmost chart, these are the frequency factor and activation energies that we decided on after doing our kinetic validation.
So now I'm going to talk a little bit about our product justification. As you can see here, we have 2 graphs, each showing 2 different cut fractions. The one on the leftmost is our gas and lights, and as well as our naphtha cut fraction. And then on the right, we have our naphtha and kerosene cuts. And essentially the way our product justification was performed was by taking a baseline of 10 components and passing those through our simulation to see where the boiling points would lie and what range of temperatures our product would boil at. And then we were able to back down those number of components from 2 and start going back up all the way to 5. And we were able to track the curvature of those lines and compare them to our base case. For most of our cut fractions, we were able to use either 3 or 4 components. And this was just due to the shape of those lines overall and how closely they fitted to our base. Next, I'm going to talk a little bit about thermodynamics and kinetic validations. So this is our thermodynamic model justification here. As you can see, we justified both the vapor phase and the liquid phase. And for these, we were able to, again, compare to literature values based off of our components and then model that with our simulator. And we were able to see that based on what we were using, the components that we had used, PSRK was our best fit for our vapor phase, which is the phase that our reactor was actually running under in our simulation model. And as well as our liquid phase, we could have either chosen from PSRK or Pang-Robinson or SRK. All of those trend relatively the same. However, we decided to go with PSRK since that's what we had already selected for our vapor phase.
And now I'm going to go into sort of how we validated our kinetics. So what you see here is an Arrhenius plot, and the way that we generated this was at each different temperature, we chose values for the frequency factor and activation energy that made the curves fit at that temperature. And these were all different frequency factor and activation energy. The challenge here was finding one set of kinetics that would work and track with temperature as it changed. So once we had modeled at each temperature some kinetics that would fit, we plotted all of these on this Arrhenius plot and were able to regress out one set of kinetics that would track with temperature. And this is just to show you sort of the results of that kinetic validation. So you can see that the trends do track as the temperature changes and as the diesel and kerosene start to curve down. In the literature, they start to curve down in our simulation as well, showing that they're being cracked into lighter products. And that continues at higher temperatures. They start to continue to crack into more of those naphtha and gas products. So now Parker's going to talk a little bit more about our safety and environmental considerations.
So one of the main hazardous issues with this system specifically is the chance of hydrogenation runaway due to the hydrogenation reactions being exothermic. And so as you can see on this heat generated versus heat release graph, you can see that once you reach around 900 up to 1,000, it does pose a problem because your generated heat outweighs your removed, and so then your temperature would just essentially continue to increase within your reactor, and it could lead to several issues such as an explosion if the temperature were to get too high. And next, this is a massive TNT equivalent for if each one of our product cut fractions as well as our flash drum hydrogen were to leak out. And as you can see for the naphtha, kerosene, and diesel, they would pose a higher impact in terms of if they were to ignite. And next we did a flammability test, and this essentially shows you the minimum flow rate that would be necessary for a plume cloud above say a line leak in order for it to become flammable. And this is based off the lower flammability limits of our cut fractions as well as the hydrogen. And as you can see, the gas would need a lower flow rate in order to become flammable, just due to the fact that it is, extremely volatile and flammable. A few other safety applications that we would consider would be explosion-proof housing, because any electronic source can serve as an ignition source within a plant. And as you can see off to the right, those are the classifications for our system specifically. And we would also need to consider a flare for, say, if we needed to flare off any of our hydrocarbons, say the hydrogen or even the lighter cut fractions that we have. And going on to the next slide, you can see that we would also, obviously a ubiquitous thing that we would need would be pressure relief valves throughout our system due to the high pressure and temperature. And for the higher temperature and pressure areas, conventional and pilot operated relief valves would probably be best on all of our vessels, because others can tend to lead to failures due to the high temperatures on the elastomer stress. And for our lower temperature areas, such as the latter half of our process, a rupture disc followed up by a relief valve is pretty common in order to handle the flow as well as the corrosion. And these are our references that we use throughout our project, and we would love to answer any questions that y'all may have.
One question, so any safety considerations taken or control schemes proposed on the feed heat interchange on the reactor?
Yeah, I can talk a little bit about that. In general, for the most part, we weren't too worried about that exchanger, primarily since the feed that we had coming in is already fairly close to the temperature of the effluent coming out of the reactor. And so that any savings that we would be making off of there would again just be kind of like a heat recycle almost. And since we were already had accounted for the material of construction needed for the reactor as well as that heat exchanger, We hadn't considered anything outside of the normal standard safety procedures.
On the heat generation and removal, the removal you calculated how?
Using the heat of reaction, the conversion.
So,
oh, you mean the removal or the generation? I'm sorry.
well, I mean, I was going to ask you generation too. So the heat generation, you got that from KimCAT, or you calculated it?
The generation was from the heat of reaction that KimCAT gave us, along with the conversion.
Okay, and then the removal.
That's what KimCAT gave us for our reactor duty.
Yeah, and in our calculations, we were using what KimCAT gave us for the reactor duty to calculate the duty of the reactor, and so they kind of went hand in hand, like our simulation and our calculations.
So the removal was from KimCAT? I don't understand how you were getting that.
Yes, sir. What KimCAT gave us for the reactor.
So the duty, the Q that it gives you for and that was linear at
Yes,
the
sir.
different temperatures?
Yes, sir.
The how much duty would you remove? You know, if you were, I mean, did you have a quench or anything that, you know, how are you going to remove it in an emergency environment?
That's how we would remove it, would be through probably a quench. We didn't have time to do those exact calculations on it, but theoretically that's what we would do. So
someone's asking, you know, that you've got a light feedstock. Maybe talk about the justification on that.
Yeah, so Michael, if you could go back to the slide with our feed. So some of the components that went into the feed would have been by themselves considered in a different cut because they were lighter or had a lower boiling point. But the goal there was to be able to match that distillation curve so that it would simulate accurately. And in order to make it match those low and high boiling points on the distillation curve, we had to include some components that by themselves would boil lower. But you can see the boiling point range shown on this slide is for our feedstock as a whole. So even though it did have some lighter components in it, it didn't start boiling actually until it got to that lower boiling point of VGO.
Did you have any regional pricing on products? I mean, could you kind of figure out where the best place to site this would be?
Just in general, from all of our components, I know the EIA.gov website cited very little regional data explicitly for you know, different locations and different components. And we didn't exactly go into that since we wanted to kind of determine a base case for our system. You know, we didn't want to specify that our reactor would or our system would only make money if we were buying this one specific kind of crude oil from this one location, since again, we're in such a volatile time right now where we didn't want to lock ourselves into any situation that we wouldn't be able to continue to make profit.
How much a day or a year did your unit make?
I would have to go and double check about that. Christy, do you know offhand?
I think there's a slide in the appendix that shows all of our total flow rates, if you can go to that. I know we starting out with 50 barrels per day of VGO and converting that, not this one. Keep going. It's probably the last one.
I think this one's the last one.
That shows you the mass flow of all of our product streams.
Okay. We're at 2 minutes over, so I'm gonna have to cut it off right there. So let's go ahead and thank our speakers. Good job, guys.
Thank you.
Thank you.
Thank you.
Andrew, are you Andrew M on the?
Yes, sir.
Okay, let me make you co-host. And we'll move on to our next.
Y'all see that?
Yep.
All right, guys. Well, hi, I'm Andrew.
I'm Kyle.
And I'm Tally.
And this is our catalytic hydrocracking system for our senior design project. A brief overview of our system. We have our VGO feed going into a series of 2 reactors along with the hydrogen feed to be reacted into the commodities being sold. Coming out of the bottom reactor, it's then going into a high pressure separator, where the tops is 85% hydrogen purity going recycled back into the reactors to be further reacted, with the liquid stream coming out of the bottom going into our low pressure separator, where the tops of the low pressure separator is going to our finished LPG, with the bottoms going into our fractionator, where the distillate of our fractionator is a mix of naphtha and LPG that will be split in this flash drum. And then they'll be sent into the respective product streams, with the middle two side streams of the fractionator being a mix of diesel and kerosene. And these will go to two respective daughter columns, where the distillates will be the finished kerosene and the bottoms the finished diesel, with the bottoms of the fractionator being the unreacted VGO recycled back into the system, where it'll be fully reacted. And we got an optimal NPV of around $78 million.
So breaking up the smaller parts of this system. So first, our reactors. We had 2 reactors, which will go into why we chose 2 reactors during our optimization section. We had a fired heater to heat up the VGO feed. We had hydrogen feed coming into the first reactor as well. And then the specifications for our reactors, they're both plug flow reactors with a temperature of 788 degrees, a diameter of 9 feet, a length of 76.5 feet. And then the pressure and hydrogen to oil ratio was set by our kinetics article with a pressure of 2,175 PSI and a hydrogen to oil molar ratio of about 4:1.
So now we've got our fractionator. You can see the schematic on the left, and on the right, we've got some of the specifications. It had a pressure of 14.7 PSIA with a diameter of 21 feet and a length of 112 feet. It contained 40 stages, with the feed stage location being at stage 20, and the reflux ratio was 11.5. And then the schematic for both of the daughter columns coming off of the fractionator being the same. For distillation column 2, which is the top distillation column coming off of the fractionator, it had a pressure of 14.7 with a diameter of 10 feet, a length of 48 feet. It contains 16 stages with the feed stage location at 11, while distillation column 3, the bottom column coming off of the fractionator, contained the same pressure with an 8-foot diameter and a length of 42 feet. It had 14 stages, and the feed stage location was at stage 6. And then we've got both our separators, our high and low pressure separator. The high pressure separator was at 1700 PSIG and 135 degrees Fahrenheit. Its diameter was 13.8 feet and its length was 41.4 feet. And the low pressure separator was at 14.7 PSIA and 100 degrees Fahrenheit with a length of 27.6 feet and a diameter of 9.2 feet. And we'll go into how we got the specs of each of these based on optimizations later on. And on the left, you can see a breakdown of our NPV, including the revenue and materials, equipment, and utilities. And on the right, we have a pie chart breaking down our revenue just so you can see how it contained each product.
So before we got our best case system, we first had to figure out what the feed and product of the reactor should be. So through research, we found that the most commonly used feed for catalytic hydrocracking is vacuum gas oil, or VGO. Particularly heavy VGO is what we used. Then from this table, we found the products from hydrocracking should be naphtha, middle distillates, which we then broke down into diesel, kerosene, naphtha, and LPG. So first, what we had to do is justify our cut fractions based on the atmospheric equivalent boiling point and then the molar mass of the paraffins, and we use all paraffins for simplicity. And then we just split the heavy VGO range to justify VGO boiling point and molecular weight. And then did the same thing for diesel with the higher end of the range of the middle distillates. And the same for kerosene with the lower range of the middle distillates. And then split the middle for the naphtha range to justify the naphtha cut fraction.
And then we put together this table showing you a breakdown of the cut fractions color-coded into each cut fraction, and you can see the molecular weight of each cut fraction, as well as for each component, the number of carbons they contain, the name, and the boiling point of each one.
So for our reaction scheme on the left there is the reaction scheme we use. We had 9 different pathways. The main 4 being breaking down VGO to diesel, kerosene, naphtha, and LPG. And then from there we had degradation reactions that broke down the heavier component cut fractions like diesel and kerosene into the lighter ones like naphtha and LPG. And then on the right, we had 28 reactions. And then on the far right there is the reaction scheme we used for that reaction. Then we used that scheme and those reactions to justify our kinetics. So our kinetics article had 6 different temperatures, and we plotted the weight percent versus residence time, and we changed what the weight percent residence time was by changing the frequency factors and activation energies in the Arrhenius equation. And as you can see for these bottom 2 temperatures, the 716 and 752, they fit pretty well. And then for 716, we got about a 10% sum of squares error. And then for 752, we got about 12%. And then the middle 2 temperatures, 788, the behavior is pretty much the same as the previous 2 temperatures. But then 806, the naphtha starts to increase as you increase the temperature up to 806. And then again, pretty good fits for both of them. And then for the sum of squares error, 788 is about 12% and the 806 about 6%. Now the top 2 temperatures were a little different. The diesel for 824 began to go down due to the degradation reactions. So it produced more kerosene and naphtha at the higher residence times. And then the same thing happened for 842, but it wasn't just diesel, it was diesel and kerosene. So we made a lot more naphtha at 842. Then for these 2 temperatures, 824, sum of squares there is about 15%, whereas 842 is about 10%. To justify our thermodynamics, we added a flash drum after the reactor and measured the hydrogen mole fraction in the liquid phase. And then the literature data is there in the black. And as you can see, PSRK in the yellow is the closest to literature data, fits pretty well, with Grayson Street not too far behind. But then we decided to go with PSRK because it fit pretty well. But then we went and did the kinetics, and it inverted all of the values for all the cut fractions and temperatures, as you can see there on the right. So we had to use Grayson Street because it gave us better fits on the kinetics and gave us right behavior as well.
So we broke down our costing here. You can see the pumps, vessels, heat exchangers, reactor, the columns and compressors. You've got the costing of the units on the tops and the utilities of each one on the bottom. As you can see, the reactor did make up the most of our cost, around 60 million, and we'll go into the material we use for that later on and the safety aspect. And that high cost is also due to the pressure and temperature. Some other high costing things included are some of our reboilers.
We then went on to our feed and product economics for the system, and we decided to use number 4 fuel oil as the VGO inlet feed for the whole system. Shown here on the left on the gray line, this was the only historical data we could find averaged by the year and only went up to 2017. And as you can see, there was also a gap between 2009 and 2013. So what we decided to do to get a more accurate depiction of what it would do over time was get the prices of 3 other commodities with a lot more historical data, those being number 1, number 2 fuel oil, and residual oil. And I found the average deviation over the same time period and used that to calculate what the average or the calculated VGO cost would be. Shown here on the right is the historical data shown in blue with the calculated data shown in orange. And then we use this calculation going on to some other data that we found that was actually average over the month rather than the year, and went all the way up to January of 2020 and did it over the last 10 years. Shown in yellow is the calculated number of fuel oil or VGO costs that we decided to use for the system. We then did this for the diesel, kerosene, naphtha, and LPG as well. As you can see, LPG was the only one lower than what we were actually buying the VGO for, and the kerosene and the diesel being the highest out of them all. So the more we can maximize the diesel and the kerosene while minimizing the amount of LPG, the higher prices we'll get. And then shown here in the table below is the average price over the 10 years and actually what we decided to use for the commodity pricing. And on top, we actually decided to use steam methane reformation for our hydrogen production or producing it on site for the reactor. And hydrogen production with capital costs and commodities that you need, methane and everything else, it costs around $1.50 to $3 per 1,000 standard cubic feet. And we averaged that to about $2.25, which gave us about 43 cents per pound of hydrogen produced. We then used the simulation as well as these pricings to optimize our reactor shown here. And we decided to use a temperature of 788 degrees Fahrenheit at a residence time of 2 hours. As you can see, the two data points below the 788 degrees Fahrenheit were the two temperatures surrounding it. So with a little bit of fluctuation in the reactor, it wouldn't really, of the temperature, it wouldn't really affect our profit that much, which was another reason we decided to use this residence time. And with this residence time, we were able to find the volume of the reactor that we needed, being around 76,000 standard cubic feet. And we found out that using two reactors half the size rather than one big reactor actually saved us about $10 million in capital costs, which brought our base NPV of 35 million up to 47 million.
After optimizing the reactor, we decided it was best to work backwards in our system to optimize the rest of it. So we decided to start with distillation column 2, which is the top column coming off of the fractionator. And the way this was optimized was by coupling the number of stages with the feed stage location. And as you can see on the right, we pulled out the optimal so you could see the visual better. It was at 16 stages with the feed stage location of 11. And this took our NPV from 47 million to about 48,300,000. And then we went on to optimize the bottom distillation column coming off of that fractionator. And we optimized it the same exact way. And as you can see on the right there, we got an optimal of 14 stages with the feed stage location at 6. And this took our NPV from 48,300,000 to about 49 million.
And for a fractionator, we coupled the pressure of the fractionator, basically the feed pressure of the fractionator and the reflux ratio. So we found that as you decrease the pressure, the NPV increases. So we got it down to 14.7 PSI or atmospheric with a reflux ratio of 11.5. And this brought our NPV up by 20 million and from about 49 million to 69 million. And then for the high pressure separator, we coupled the pressure and the temperature. And after 135 degrees, the optimal pressure was higher than the reactor pressure. So we couldn't really go above 135 degrees. So we decided to cap it at 135 and then found our optimal pressure to be about 1700 PSI. And that brought our NPV from 69 million to 77,200,000.
And lastly, we went on to optimize our low pressure separator. We decided this couldn't be coupled with anything due to the fractionator already having the pressure being optimized. So we only optimized the temperature. And as you can see, the optimal temperature ended up being 100 degrees Fahrenheit. And this raised our NPV about 500,000. And as you can see at the bottom, from base case to optimal, we went from 35 million to about 78 million.
So for our first safety consideration, we found the heat produced from the exothermic reactions versus the heat removed, and the heat produced was exponential using the Arrhenius equation, and then heat removed was linear. And then on the left there, the graph starts on the reaction kinetics article temperature we found at 716 and goes up past what we used for our temperature in our system. And then on the right, it's a little zoomed in, and then once the heat produced passes the heat removed, that's when you have the potential for a runaway reaction. And that temperature is 883 degrees. So anything after that, you would need more flow rate of quenched hydrogen into the system to cool it down and prevent a runaway reaction.
The last safety aspect we looked at was the phenomenon high temperature hydrogen attack, which happens hydrogen at certain high temperatures and pressures inside a vessel made of high carbon content. The hydrogen can actually diffuse into the vessel's walls and react with the carbon, creating methane gas, which can cause small cracks inside the vessel. And then over time, these cracks can get larger and larger and larger and larger and possibly cause a catastrophic failure. And as you can see on this Nelson curve shown here, it is much higher than the metallurgical limits of carbon steel. So what we decided to use for our reactors, metallurgy, was chrome steel with a stainless steel welded overlay. And those are our references. Any questions?
We got a couple of questions. One first that I wanted to ask, you had a reflux ratio of 11.5 for your fractionator. Could you show me what your utilities were for that, both in the, reboiler and the, I guess the condenser?
So it's going to be the condenser 1 and reboiler 1.
So 3 million and 6 million?
That'd be the
Oh, condenser 1, 246?
Yeah.
Wow, that seems low. So that's cooling water, I guess, right?
Yes, sir.
Correct.
And then what's the utility on reboiler 1?
Tally, what did we decide to use?
I believe for that reboiler, we did it as a fired heater.
And then let's say your heater was 3 million. So I'm just surprised that a reflux ratio of 11 was the optimal there. You got some questions. The residence time appears to continue past the chosen optimal. Why was the optimization stopped there?
The reasoning behind that is because that was actually when our simulation stopped. That the data for our article stopped, and we didn't feel like we had the ability to go past the residence times and temperatures that we were going off of for our simulation. So we didn't think that would accurately depict the profit and NPV.
Do you anticipate any control problems for the towers? You've got several of them operating at atmospheric pressure.
I'm not sure we really thought about that, but with more time, we could go into that and figure out the answer to that question.
Sure. Other than a runaway reaction, what other environmental or public health factors did you consider?
Just the high temperature hydrogen attack that could possibly cause the catastrophic failure of the vessel.
So no other environmental factors that you thought of?
No, with the time crunch that we had, we didn't really get into as much as we wanted to, and that was one thing that we'd go into more as well.
Okay. I'm not seeing any other questions. We're at 2:01, so let's go ahead and thank our speakers. Good job, guys. Yay. All right, with that, so I'm going to leave the meeting open. You guys can, mute and stop sharing. You can actually, stay here, though. I don't know if everyone starts talking or something, it'll probably get kind of crazy. We're going to start back at 2:20. So the teams that are going to present, why don't you guys check back in, pop back into the video and everything about 7 minutes prior or so. So I can hand that off and get y'all set up as co-host and everything. But I hope to see everyone else back here by 2:20. Thanks, guys.
Thank you.
Thanks, man. You're welcome.
This might be a really dumb question, but what is a fractionator?
Anybody want to answer that?
It's open to anyone.
I'll take it.
Well, thank you for watching.
So fractionator was let me turn my video so you can see who's talking. Fractionator was a term that we used to describe a distillation tower with multiple side streams coming out of it. Just because it's splitting it instead of just like a top and a bottom stream of separation, it would have like maybe one or two in the middle as well.
Okay, thank you.
Any other questions from the audience?
Having flashbacks to my design, Dr. Palmer. All this wells and cracking and detonators. Grabbed my report. I was like, oh man.
No, my design was something with like chemical grade butanol or something like that made from corn. I was like, I never want to hear butanol again. And then my job at college was 4 years as an engineer in the butanol plant. So,
oh no.
but now I'm doing all this hydrocarbon stuff. So now it's current.
Yeah.
I'm happy with plastics. I'm good.
Dr. Palmer, do I need to make you the host again, or is there anything?
No, I'm still a host. I can take you off of co-host. So.
All right.
Wow, we got 52 participants, or people that are attending and everything. We had up to 66 at one point. So I think there's a lot of positives of having the online, at least in the these final presentations.
Yeah, I think that was really cool. I got to have like my family and then like all my friends from all over the country watch. And they wouldn't have been able to make it to Ruston for the time being.
Yeah, sure. That's cool.
I do like to look at real faces though sometimes when I present, but yes, the Zoom is very beneficial in like the being able everyone to come and see.
Yeah, someone suggested maybe a live stream next time. That's probably, I imagine, if we're able to present in person, that's what we'll do. But, a live stream might be a way to do that. We'll set up a Facebook live stream. Hey, Alex and Darius, I'm not seeing the Quentin on there. I was gonna go ahead and set him up as co-host as well so that we can transition a little quicker after. Can you guys, text him or?
On the schedule, it says that we are at 2:40. That's probably why.
Yeah,
Just Chance and Elizabeth and Pravesh are next. But I mean, if you need us to go now, we can go.
no, not go now, but I'd like to set up all the co-hosts so that
Okay.
we can seamlessly.
Okay, I got you.
All right, and Dr. Palmer, my laptop webcam wasn't working, so I'm using my desktop to share the screen with y'all, and I'll be using my iPhone so you can actually see me and hear me.
Okay, I wondered about that.
Yeah, so that we could actually get a video.
Two-minute warning to everyone. There you are, DeQuinn. So the other group's going to present first, but I did want to go ahead and set everyone up that's going to be co-hosts. So. All right, 1 minute warning. Or maybe less than that. So if anyone is just now joining us, we've got kind of probably some transitions in the audience and everything. So we've got our senior design group. We've got 3 more groups on this session and everything. We'll have about 20-minute talks. They're going to be presenting on a vacuum gas hydrocracker that they sized and optimized and everything as part of their senior design. And so we're up at 2:20, so we can go ahead and have our first team present. Go ahead, Chance.
All right, y'all ready? All right,
Yep.
So today we're going to be presenting our hydrocracker processing unit that we've designed over the past few quarters. My name is Chance Donahue.
I'm Elizabeth Ezel.
I'm Pravesh Pokral.
All right, and so this is our presentation. So first we'll start off with just the system overview of our entire unit, starting with the process flow diagram. So here you can see that we have 2 feeds incoming. We have the hydrogen and the VGO. The VGO enters a preheat exchanger that utilizes the reactor effluent to heat it up. That way we don't have to use as much energy before sending it to the reactor. That VGO stream then enters the reactor and exits as effluent stream. After passing out that first heat exchanger, the reactor effluent then enters the second heat exchanger where it's further cooled by the feed from the number 2 flash drum. After that, it then enters a cooling water heat exchanger, and then finally a 4th exchanger where it is cooled off using medium temperature refrigerant or medium temperature cooling water. So at this point, the reactor effluent's at about 70 degrees Fahrenheit. And when it enters the flash drum, all of the hydrogen is flashed and only a small portion of the gas is flashed off. So that stream is then sent through the recycle compressor and sent back to the reactor to be re-reacted. The liquid from that first flash drum then leaves. It goes through an expander where it drops in pressure from 150 bar down to just 1 bar. And it then enters a heat exchanger and then goes into the second flash drum. After entering that second flash drum, all the gases are stripped off the top or flashed off the top, and all you're left with is the liquid stream of the naphtha through VGO product streams. And so that stream just enters our series of distillation columns to be separated out. An important thing to note is that the entire process before that second flash drum is kept at about 150 bar. So this makes it where our recycle compressor can be significantly smaller, since it's not having to bring it back up from atmospheric pressure down to 150 bar. And it's only that makeup hydrogen compressor that's having to do any serious compressing work. All right, so now for the safety considerations. So since we did have that heat integration with the VGO feed, we wanted to add a bypass line around it. So that way we wouldn't risk the having a runaway reaction. And so by utilizing a bypass, if the reactor starts to overheat, we could bypass the VGO around that exchanger and deliver relatively cool VGO feed to that reactor bed, so we'd quench that reaction before it starts to run away. In addition to that, we'd also like to add a lattice of temperature indicators around the reactor bed, so that way we could more closely monitor how the reaction's going and maybe monitor any hotspots that might be occurring. We're even be able to tell if there's a cold spot in the reactor bed, we might be able to just troubleshoot and determine if it was, say, channeling or coking possibly forming. For safety considerations, we wanted to look at the possibility of both hydrogen embrittlement and high temperature hydrogen attack. It seemed like the high temperature hydrogen attack was the only real threat to our unit. And so shown on the graph on the right, you can see where our the red line depicts the operating range of our unit. So depending on what temperature we use for the reactor, it could be anywhere on that line. And you can see that line is well above the minimum that the carbon steel is rated for. So moving forward, we decided to use stainless steel for both our reactor and that first heat exchanger right after the reactor, so that way we don't have any high temperature hydrogen attack occurring. All right, so now for our environmental considerations, as well as this is also an economic consideration, we decided to add 2 points of heat integration. One is going to be that first reactor, or the first heat exchanger right after the reactor, and the second one is going to be the second heat exchanger. And so by utilizing these 2 exchanges, we're able to save about between 6 million to 2.6 million gallons of year in fresh cooling water. And that range is just kind of dependent on how many cycles you could get out of your cooling tower's cooling water. All right, so now for the thermodynamic justification. So the shown on the graph below is a graph of the the volatility of our feed based on how much or how many carbons are in the carbon chain. And so you can see those blue X's denote the reference data, whereas all the other points denote any sort of denote our simulated feed data based on which thermodynamic model we were using. So you can see we used Unifac, Grayson-Street, PSRK, Uniquac, and Ping-Robinson. And out of all those, it seems like the Uniquac was the best fit. So we decided to use the Uniquac moving forward.
Right now we have our feed components, which we chose based off of their carbon numbers and their boiling points. So each component of making up the VGO has their boiling points listed here from the lowest to the highest. It was also found that VGO typically consists of about 27.4% aromatic compounds and 72.6% non-aromatics. And then next we have our product components. These are also organized from the lowest boiling point to the highest. We had about 4 components per cut fraction. These are also chosen based off of their carbon numbers and boiling points. And now we have our graphs of our kinetic model versus our reference data. These graphs, the points on the graph represent our reference data, and our dashed lines on the graph represents our model. We modeled 4 different temperatures and 4 different residence times. The residence times were about 30 minutes, 40 minutes, 1 hour, and 2 hours. And the temperatures were 752 degrees Fahrenheit, 788 degrees Fahrenheit. This is 824 degrees Fahrenheit and 842 degrees Fahrenheit. Now
Next,
we'll go into,
okay. Next, I'm going to be talking about a unit of costing and specification. First, we can talk about reactor and flash drums. Our reactor was quite huge with a diameter of 28 feet, height of 238 feet, with a volume of 143,000 cubic feet. The total CBM of our reactor was $412 million. The material of construction for the reactor was stainless steel to avoid the hydrogen attack at higher temperature. Our first flash drum was quite expensive with a CBM of $4.5 million. And then second flash drum was less expensive because of the less flow rate going into it with a CBM of $231,000. The material of construction for both flash drums was a carbon steel. Next we got compressor specification. We had two compressors. It's a chance mentioned earlier, one for hydrogen recycle, one for hydrogen inlet feed stream. We got the efficiency and power straight out of ChemCAD, and the total compressor CBM was around $3.7 million. Next, I'm going to be talking about tower and surge tanks. We had a total of 3 towers in our system, with tower 702 being the most expensive of all, with a CBM of $7.2 million. The total number of actual trays were 62, with a diameter of 6 meters and height of 41 meters. And the third tower, that is tower 703, was least expensive of all because of the very less flow rate going into it. Since more than 95% of our VGO was already reacted, we thought about getting rid of it, but to maintain the higher purity of diesel and the CBM cost was just a fraction of the total tower cost, we went ahead and kept it in our system. And our first flash drum for first tower was 24 meters cube in volume, whereas the last one was just 2 meters cube because of the very less flow rate going into the system. Next. So we had total of 10 heat exchangers in our system, with heat exchanger 701 and 702 participating in heat integration, as Chance mentioned earlier. We cool down the reactor effluent stream by using an inlet VGO flow rate, which was further cooled down by the stream coming out of the first flash drum down to around 397 degrees Fahrenheit, which was further cooled down by using cooling water by using heat exchanger 703 to 150 degrees Fahrenheit. And then we use heat exchanger 704 to cool it down to 70 degrees Fahrenheit by using moderately low refrigerated water. And so these are the heat exchangers we used in our tower, with deboiler and condenser in each of them to heat any process steam more than 500 degrees Fahrenheit. We use natural gas fired furnace with some kind of heat exchanger fluid like molten salt, which doesn't crack down in higher temperature. And to cool down some process steam, which was more than 300 Fahrenheit, we use cooling water with some kind of heat exchanger fluid like diatom. With a total, hereby we have a total heat exchanger CBM of around $1.28 million. Here is the total FCI breakdown of the total unit of costing and specification. The majority of the FCI was contributed by Reactor. As you can see, more than, like, I would say around 90% of the total FCI, and tower came in second with $10.6 million, and rest of the process equipment contributed very less to FCI, as you can see in the pie chart. This is the total utility breakdown for the system. Around 58% of the total utilities was used by heat exchangers, whereas the reactor used 38% of the total utilities, and compressor and pumps coming in at second and third with 2.9% and 1.1% respectively. The second table lists the various types of utilities we used in our unit. Next, we're going to be talking about the optimization. The first optimization we did was reactor optimization. So we used reactor residence time and the temperature coupled together to find the optimal NPV value. As you can see, our optimal NPV value was around 2 hours of residence time in 824 degrees Fahrenheit. It was the second highest temperature where we got our optimal NPV. Although we validated our kinetics for up to 2 hours, but we didn't see any dip in our graph. So we went ahead and did the calculation for 2.5 hours residence time, where we actually saw NPV going down, keeping our optimal point at 824 degrees Fahrenheit in 2 hours. Yep.
So for each of our distillation columns, we coupled the number of stages and the feed stage location to find the optimal point. So we varied the number of stages with feeds at 1/4, half, and 3/4 of the way down the tower. T701 was our tower that separated our diesel and VGO from our naphtha and kerosene. And its optimal number of stages was found to be 16 stages with our feed halfway at the 8th stage. T702 was our tower that separated our naphtha and kerosene. We performed the same optimization and found that the optimal number of stages was 36 stages with the feed halfway at the 18th stage. And T703 was our last tower that separated our VGO and diesel. It didn't have much of an effect on our NPV, only about like $200,000, I want to say. But the optimal number of stages was 24 stages with the feed located 3/4 of the way at the 18th stage.
All right, so now I want to cover some of the topology optimizations that we made over the course of this quarter. So this is one of the more recent ones, about a week ago. Our NPV was at $430 million. And the biggest difference between this topology and our current one was the fact that we had 4 distillation columns in this one. You can see that 4th distillation column separates out the naphtha and the gas. And so instead of having that relatively incompressible gas stream go through all 3 of these columns, we instead decided to add a second flash drum before Tower 1. So we're able to remove that gas stream out. And so it eliminated a distillation column and also reduced the size of our distillation columns. And this is just showing you, again, our current topology. So you can see it's at $590 million. So that's about a $160 million increase. And we're able to do that by removing that, as I said, that 4th distillation column, adding a flash drum, as well as some other smaller optimizations. All right, so now for the commodity costing. So this just explains how we got the pricing of our streams. So first is VGO. We were able to find it using EIA.gov. We took a 10-year average from February 2010 to February 2020. And we were able to plot that out. And so that gave us the price for in dollars per gallon. However, we also needed to convert it to dollars per pound. So we divided the price by the density of water as well as the specific gravity of the VGO. And we're able to get a price of $0.214 per pound of VGO. Hydrogen was a little bit different. We weren't able to find any direct listings for hydrogen from EIA.gov. However, we were able to find on refinerlink.com. They had an article where it said that if you were to have a steam methane reformer either in your refinery or you had access to one, you were able to get hydrogen typically around $1.50 to $3 per 1,000 standard cubic feet of hydrogen. And so we decided to pick a price in the middle of that range. So $2.25 per 1,000 standard cubic foot was chosen. We then converted that to dollars per pound to get a total cost of $0.432 per pound of hydrogen. Diesel pricing was the exact same as VGO. So we're able to just take the 10-year average and find from EIA.gov and find it to be $0.324 per pound. Same thing with kerosene. We're able to take that 10-year average, and for kerosene, the pricing was $0.341 per pound. Naphtha was a little bit more challenging. They didn't have that listed, so we were able to find it, however, on tradingeconomics.com, that it listed in dollars per ton, and so it took the 10-year average, and I was able to find a cost about $560 or $650 per metric ton. We then converted that to dollars per pound, and we're able to find a total price of $0.29 or $0.295 per pound. And then finally is the gas pricing. So we're also able to find this from EIA.gov, and we found it to be about $0.22 per pound for naphtha.
So here's just a breakdown of our NPV. So you can see that our revenue from our product streams and the cost of our raw materials affected our NPV the most out of all of the costing factors, with the FCI not far behind. And our NPV was about 590 million.
All right. So now open up the floor for questions.
Yeah, so we've got a question about, are you aware of any kind of issues of impurities getting into the hydrogen on your recycle impacting your system?
As far as getting it to converge, or are talking about just too much hydrogen accumulating in the recycle?
No, not the hydrogen itself, but you know, are there any other components that could be in there that you need to be, you know, make sure that you're improving? You know, something that might affect the chemistry or you know, impact, you know, the reactor in terms of, you know, your conversion and everything.
So the only thing we noticed that we'd have a buildup of is ethane, and that's just because we'd have to get it to too low of a temperature to be able to condense it. However, we didn't find that enough of it was recycling that would cause too much of an issue. So, and also it wasn't reacting any further. So
yeah, so it may not have been something that you were, you know, specifically modeling and all, but I mean, in your literature studies, did you find anything where, you know, that might have suggested, oh, I've got to maintain, you know, the purity of this below X or whatever?
We didn't find anything directly, but that is a good point. There might be some nitrogen compounds or some other compounds that might poison the catalyst that we need to look out for. So
yeah, they're suggesting CO2 is some concern. So any ideas of your expected catalyst life?
We didn't find any direct sources as far as how long the catalyst should last. However, I know just from industry experience, the hydrocracker catalysts usually could last for up to 6-year periods in between the shutdown for turnaround. So, but we didn't directly look it up.
Yeah. So on your cooling water, you had 2 heat exchangers that you were cooling, and you said cooling water or Dow-therm. I'm assuming what you're doing is you're going Dow-therm through the heat exchanger that you're showing, and then you're calculating the cost of removal based on the cooling water. If you do that, I mean, and you can correct me if maybe you did this differently, but if you do that, you're going to have to size 2 exchangers, right? Because you've got one exchanger that the Dow-therm goes through and everything, and so then that's going to be oil to oil in terms of your heat transfer coefficient, and then you'll have oil to water, and you've got to get a whole nother heat exchanger. Did you consider that you needed 2 heat exchangers there?
Actually, what I did was went back to the book, and I just followed one of the process units in the book that they just showed a schematic diagram of how they cool down temperatures at higher temperatures. So they were just showing they use some kind of Dow-therm fluid, and then they use the cooling water to cool the Dow-therm. So that's a good point to consider for the future.
Yeah, I mean, because you got to send the Dow-therm through something, right? It's got to go through a heat exchanger. So you need to size and cost out that second heat exchanger if you're going to do that. Your reactor size was 28 feet in diameter, 238 feet tall. Did you look at, you know, breaking it up into anything else, you know, multiples or anything? Was that more expensive, or did you try that?
No, we didn't explore breaking into multiple reactors.
Any safety considerations that you went through?
For what, breaking or?
I mean, just in your design and stuff. One of the questions someone's asking is.
Oh yeah. So some of the safety considerations that we had was, you can see on this picture that X701. That's the preheat exchanger for the feed. And if the reactor would start to run away, if we didn't have a bypass around this exchanger, we wouldn't be able to control the temperature. So one of our safety considerations was to add a bypass around the preheat exchanger. So the relatively cool VGO could go directly into the reactor bed and quench it. That's one of the safety considerations that we had, as well as just the material construction safety considerations.
You didn't calculate the runaway, like how much duty and stuff?
No.
Okay. All right, I think we're at 2:42, so let's go ahead and thank our speakers. Thanks, guys. Yay. Next team up. We got Quentin, Darius, and Alex.
Yes, sir. Yes, sir.
You should already be pre-shared as co-host.
Okay. Give me 1 second, please.
Yep.
So this is our hydrocracker design report. I'm the Quentin guy. I'm Darius Smith. Alex. He's mute.
I'm sorry, I'm Alex. I was on mute.
So we're gonna just a quick summary of our report. We're gonna go over the introduction, some design for our hydrocracker system. We're gonna go through an evaluation of our NPV, some of the optimizations that we've done, as well as we're gonna give some supporting information to the audience on how we got to the numbers that we got to. So just an introduction before we get into everything, some of the quick numbers. We had a net present value of 620 million. And as you can see, we had a revenue of about 4.1 billion, raw material cost us 3.1, and we'll go deeper into these numbers as the presentation goes on. So here's the overall design. As you can see, we have one single reactor, a hydrogen recycle, a high pressure separator, a low pressure separator, as well as 4 distillation columns. If we just take a look at the reactor section, we have our reactor product sends out over 600,000 pounds an hour of a mix of both unreacted VGO as well as our products, as well as the products that we've made. That goes into our first high pressure separator, which helps us recover most of our hydrogen. And then we purge off mostly butane that was unrecovered in that hydrogen stream. And then we send again that mix to another, yet again, a low pressure separator, which goes on to our towers. Okay, so next we have our first 2 towers. Our first tower is separating our middle cuts from LPG and naphtha on going up to the distillate product, and our kerosene, diesel, and unconverted VGO going out the bottoms of that first tower. Going to the second tower, that's where we separate our LPG from our naphtha. Next slide, please. Next, the third tower is the bottom product of our first tower, which separates our kerosene and diesel from an unconverted VGO, which should be sold as resid. And our fourth tower separates our kerosene from our diesel. And this is just an broad overview of our equipment. We have a 53,000 cubic foot kinetic reactor with a zeolite catalyst, an 8,500 cubic foot separator, that's our high pressure separator, an 1,800 cubic foot separator, which is our low pressure separator, 4 distillation columns, 4 compressors, and 5 pumps. And this is our reactor sizing. So initially we couldn't size the reactor due to our equation in the book due to the high volume and high pressure. So we used an equation that Dr. Palmer provided with us as we found our effective diameter and height of the reactor. This equation already factors in our pressure factor of 2200 PSI. Yeah, that's good.
So our tower sizing was determined by first calculating the cross-sectional area of the tower. We use that cross-sectional area to determine our volume by multiplying by the number of trays and the tray spacing. Next calculation was the heat exchangers. We sized the heat exchangers by using the log mean temperature difference method. And as you can see, there's the cross-sectional area. It was priced by using the cross-sectional area as well. For our pump sizing, we use the mechanical energy balance, also known as Bernoulli's. As you can see, we did our equations. We found the Reynolds number to determine if it was laminar or turbulent flow, and from there determined our friction factors and other variables, whether they're neglected or not. And then our compressors, we size our compressors using the adiabatic reversible compressor calculation. For the fired heaters, which we use as a substitute for some of our reboilers, so because we couldn't get high enough utility temperatures, we pretty much priced these by using the heat duty on our reboilers and our columns.
Okay, so now for our thermal justification, we did some research and reading around to see which thermodynamic models would be best for our VGO feed. And we read that the models such as Ping-Robertson and Grayson Street were suitable models. However, we couldn't find any thermodynamic data for Grayson Street, so we decided to see how Ping-Robertson behaved within the system and versus some thermodynamic data we found. Next slide, please. And as you can see, we found systems of pentane and dodecane, which are both components found within our system at atmospheric pressure and below atmospheric pressure, since we might be using vacuum distillation columns. And as you can see, the black dots and the gray X's represent our simulated data from KimCAD, which corresponds to the green and red lines, which is our thermodynamic data we found from literature. And as you can see, since the curves are pretty much lined up, we decided to use Ping-Robertson as our thermodynamic model. And going on to our reactions, we have 8 reactions, 2 of which produce our LPGs, 2 produce our kerosene, 2 produce our naphtha, and 2 produce our diesel products.
So here's just a rundown of our kinetic values. These don't mean much to you just looking at the numbers, but they mean more whenever we compare them to our literature data. This data was compared at 380 degrees Celsius or 716 Fahrenheit. So this, we're going to show here how it lines up with residence times, and we're going to talk about more why we chose to go with an hour of residence time as we get closer to talking about our products. So as you can see, our KimCAD simulation lines up pretty closely to the literature data. Our diesel trends slightly above, and so does our kerosene, but with it's about a 1% difference on each. So here's just a table of our conversion, just to give you a rundown on what our reactor is actually producing. As you can see, as temperature increases, we start to create less diesel when using the kinetics that we modeled from our literature. And that led us to go to use lower temperatures, because if we start to create less of our high commodity products, our NPV starts to go down.
Okay, so one of the major safety aspects that we considered in this project is obviously thermal runaway. So as we research runaway reactions, we pretty much, found what are the main heat sources, as you can see in that table, and heat sinks, as well as different removal mechanisms and how effective they are. As you can see on the bottom chart, they have other many temperature excursion methods. One saying to depressurize the reactor, which is very effective, but we found that would definitely give us worse product yield. So we definitely said the best way to prevent our thermal runaway was a hydrogen quench system. So the way we figured this out was, as you can see on this graph, we have that first curve, the blue curve that shows our reactor heat generation that comes from our reactions, which was calculated through KimCAD. That was the heat we found from KimCAD. And that orange area is where we find that it becomes unstable around that 1200 degrees Fahrenheit region. On the red curve is our heat removal rate, which was determined using our convective heat transfer equation between the hot reactor fluid within the reactor and the surroundings, which includes the new feed that enters the reactor, as well as the reactor walls. now I'm thinking about it, we possibly could have also considered the heat that is removed by the catalyst, but I didn't have enough of information to determine that. But as you can see, the heat removed is able to, the amount of heat that can be removed from the reactor stops at about 720 degrees Fahrenheit at about 250 million BTU. So that's where we knew that's where we had to determine how much hydrogen we needed. Right here is a calculation of the amount of hydrogen we needed. We started off by doing an energy balance, determining how much heat removed we would need by the hydrogen quench, and then calculated the amount of mass from the hydrogen using our MCAT equation. And we got a total of 25,000 pounds per hour of hydrogen we would need to quench the system.
So just a little more about process safety. We're going to talk a little bit about the control schemes we plan to employ for our hydrocracker. So during our research, we've seen that many people recommend having a fault tree. That way you can control many different emergency outcomes that happen within the system, as well as using that fault tree to incorporate an auto depressurization scheme in order to prevent overheat due to a runaway reaction. Depressurization is just would be just a backup plan to a hydrogen quench, because a hydrogen quench preserves the system and the products that we're trying to make, which is why we did the calculation on a hydrogen quench. But automating some of these steps and not allowing for an operator to miss his cue or to overthink the system could help keep the safety of not only the operators but the system itself. Likewise, we took a little bit of a look into instrumentation, and it seems that it's pretty standard to install internal pressure gauges that will not only tip you off to a runaway reaction, but will also tip you off to a leak in the reactor. Hydrocarbon gases pose a large fire and explosive risk if they begin to leak due to some type of corrosion through the walls of the reactor. So it's something we should definitely watch out for. And we also would stress the importance of having valves fail in the correct position and allowing temperature systems throughout the reactor so that we know if a runaway reaction is on the rise. Finally, we just cover some safety on maintenance and operation as well, just for the safety of our employees working around the reactor. There's a lot of caution when it comes to unloading the catalyst, and catalyst should be allowed to cool to 120 degrees Fahrenheit in order to prevent sulfide fires, as well as they pose an emissions hazard above that temperature due to various hydrocarbon gases and gases containing sulfur. And then for operation, due to the presence of hydrogen and sulfur at high temperatures, corrosion is very possible. And we chose to inject colder hydrogen into our reactor in order to prevent a runaway. That way, it makes it less of a risk of happening.
Next, we'll talk about the evaluation of our MPV. We'll begin by our revenue. We made a total of 4.1 billion per year. And as you can see, we're making 600 million a year based on our diesel. One interesting thing is that we're making more money off our resid, that are unconverted VGO, than our other products. Our operating costs, as you can see, the big chunk of our operating costs comes from raw materials. Our fixed capital cost, which is our equipment, just takes about 28% of that, of our total costs. And right here, you can see a breakdown of our FCI. Our main FCI is our reactor, and that's obviously due to the size of our reactor. We have a large reactor, but as well as the pressure factor on the reactor as well. And you can see that the reactor is priced at $220 million.
Our next most expensive piece of equipment after our reactor is our second tower, the tower which separates our LPGs from our naphtas. This tower had to be a very large tower, not due to the amount of flow, but due to the very rigorous separation that's going in. We have some residual hydrogen coming in to that stream, so we couldn't have a smaller tower to just separate that. Also, the volume of the reactor is pretty large due to the 50 stages and the diameter of the reactor. And this is a breakdown of the cost of that reactor system, with the tower costing about 2.4 million, the trays costing about $200,000, the condenser, and the fire heater. We had to use a fire heater because we couldn't find a utility hot enough in order to heat that reboiler. So we just took the duty and sized the fire heater that way. And we have a surge tank. And this is how we came up with our raw material. We had a spec of 50,000 barrels a day. That wasn't just recycled VGO. That was fresh VGO that we had to feed into our system with a target API gravity of 24.5 with this density of 55 pounds per cubic foot. Is how we came to a feed of 550,000 pounds per hour of VGO. And the literature we used specified that we had a ratio of 800 normal liters of hydrogen to oil. So we converted our hydrogen to about 5.1, which is 51,000 pounds of hydrogen per hour. And this is the commodity price we found for our VGO. Was buying it at 19 cents a pound, and we're buying hydrogen at $2.70 a pound, which caused us a raw material cost of 3.1 billion per year.
So during our optimization, we're going to talk about where we thought we could best improve the system and what steps that we take in order to improve it. From a topological standpoint, we attempted to run a twin reactor setup. We assumed 2 reactors would be cheaper than 1 large one, and that it would be helpful for turnaround and would help us develop simpler kinetics. It didn't really have much of an effect on kinetics, and the reactors had similar conversion after all. But having 2 reactors actually resulted in a $20 million lower NPV than having both, as well as it led to more mass balance errors within our KimCAD simulation to keep 2. So we switched back to the 1 large reactor. And then reactor info, I'm sure many people wondered why we didn't recycle our unconverted VGO, being that, and even though we were making so much money on resid, the system had mass balance errors above a 10% recycle due to the complexity of the kinetics as you increase recycle. So every more maybe 10,000, 100,000 pounds of VGO that we recycled, the kinetics had to be tweaked further, had to be more precise, had to be readjusted. And it had gotten to the point where it was more economical to not recycle any of it rather than and to just let it be sold as resid. So as you can see, our NPV with the recycle was about around the $450 million mark. But when we took it out and decided to sell it as resid, we got 600 million plus before optimization. So for the reactor, the one optimization we did do was around temperature and pressure. As you can see, we only did between 110 bar and 140 bar. We attempted to stay true to the literature by not straying away from any pressures that it had not tried itself. And so we capped the system at 140 bars, which as you can see was the most optimal. And the line for 110 bar was missing due to the mass balance errors created due to an error in kinetics.
So moving on, we decided to see how to optimize our distillation towers. So in our first tower, we decided to first see what's our optimal specs as far as purities. As you can see, we have a purity of 99.9% on our distillate and 99.9% of recovery in our bottoms. Next. And using that purity spec, we decided to see what's the best location for our trays and at what pressures to run them at. And it was shown that for the first tower at atmospheric pressure with 10 stages, the optimal feed tray was at tray 8. Moving on to our LPG and naphtha tower, we couldn't specify the purities schemes in that due to convergence errors in KimCAD. So we decided to look at our reflux ratios and our bottomless molar's feed rate. There wasn't much difference, but there was a optimal point at about a reflux ratio of 3 with a bottomless molar flow rate of 60 moles per hour. And we performed the same optimization as the previous tower. We're looking at the feed tray locations and at the pressure. And with this tower, it was actually at a lower pressure that we would was most optimal for this tower, with the feed tray at tray 29 out of 40 with the pressure of 0.8 bar.
So for tower 3, we used a similar approach as that first tower as far as optimizing. We took our fraction recovery and our distillate and compared it with various fraction recoveries in our bottoms versus NPV. And as you can see, our optimal value is at 99.8% in the distillate and 99% in the bottoms, which makes sense because we have more valuable product in our distillate. Same thing for tower 4, separating the kerosene from diesel. Same approach, optimize the NPV by using by graphing our fraction recoveries in the distillate at various bottoms component for fraction recoveries. And as you can see, it looks a lot like the same graph from tower 1. We found an optimal value of 99.9% in the distillate with a 99% bottoms fraction recovery, which also makes sense because we have more valuable product in our distillate stream.
So here's some supporting material we're gonna go over. And at first we did a sensitivity study on the system to show what our system was most sensitive to. And we did a 10% change on each parameter. And as you can see, the cost of raw materials is what really manages the NPV of our system, being that a 10% increase in raw material costs would result in an almost 90% decrease in NPV, while a 10% increase in revenue would only result in a 50% increase. So our system is very raw material dependent. As well as in order to relate the system to similar times as we are in now, but with data that's more well established, we compared our system to the oil market during the Great Recession in late 2008, early 2009. So here are the prices that were averaged from about October of 2008 to April 2009. And when compared to our system, our NPV went from about 620 million that we are now to negative 160 million due to low demand. And following this are the graphs containing the data that we used in order to come up with our commodity prices. As well as stream tables from our simulation itself. And now we'll open the floor for questions.
Yeah, so we've got a few questions about the the recycle and your VGO pricing and expectations there and everything. Let me see how to maybe wrap that up together. What do you feel like? I mean, so what was the recycle rate or amount of VGO that you were seeing in the literature? Was it as low as I mean, did they not recycle it? Were they producing as much revenue from their VGO as what you were seeing?
You're asking about the literature, correct?
Yeah, I mean, and when I say literature, I mean what I'm referring to is most of the other commercial hydrocrackers or anything else that you saw out there that was operating. Did other units typically operate at low or little or no recycle of the VGO?
No, sir. One would expect that in a typical hydrocracker setup, you would recycle as much as possible, and you'd find a use for what you could not. Our literature that we have built our kinetics on and speculated our data from does not mention a recycle, nor does it talk about reintroducing the unconverted VGO. So when it came to modeling our kinetics to follow that information, incorporating a recycle did make it more complicated.
So moving forward, let's say you had additional time and everything like that. What would you do to kind of attack this problem? Where do you think the problem lies, and where would you spend your time trying to, quote, fix it?
I would say one of the major issues with that our recycle is because what DQ said, our kinetics in the reactor. One thing that we definitely looked at and we wanted to implement, just didn't have enough time. It was towards the end, was possibly using a second reactor, but using a second reactor solely to recycle our recycle stream and adjusting our kinetics to just that recycle stream, so that we wouldn't have to continuously adjust our kinetics. So that I think that would have been really effective, and then it would have been a much smaller reactor as well, most likely. So I think that would have been a good route to go.
How many components were you feeding in to represent VGO, and then how many of those were reacting?
We put in 9 components and all 9 reacted.
So all 9. So everything that recycled back should have reacted. Then, is that right?
No, sir. All 9 did react, but I'm not saying that all 9, reacted completely. So of course, there were some that reacted better than others, which led to the recycle being harder to implement.
Okay, so as you were tweaking your kinetics, maybe some of them, weren't at a high enough rate to be representative. That was masked then in the total. I see.
Yes, sir.
So, one question on your. Is there a point if you lost your hydrogen flow, your hydrogen, to cool down the reactor, what would be the temperature where you would expect there to be a runaway?
1200. It's right when on that unstable curve, that orange curve, it's around there. I would say that's where we found it to be. But it could possibly be lower than that because, as you can see, the heat removal rate is at a much lower temperature. So it could be at a lower temperature. Yeah, that's actually what I was getting at. Hey, I think anything above that red line, you're relying on your the cooling from the hydrogen. So. Yeah, when I made that curve, I definitely looked at. I didn't do the heat removal curve until I made that the blue and orange curve. And just based on what I saw from other literature, it kind of showed whenever you've seen a second spike, that's when you're kind of entering that runaway. So I possibly should have looked at it further once I created the heat removal rate curve and seen that, okay, well, we can't remove any more heat after this. This is probably when we need to implement our quench. So if I were to redo it, I'd probably say around that temperature, like at 800 degrees Fahrenheit. Yeah, typically you're actively running a quench and everything and all. And so, just to operate anyway. And so otherwise I think at one point you said something about, heat removal from the catalyst. Was that, were you misspeaking or was that, did you expect to remove any energy from the catalyst? Well, like you can see in that table, if you can go back to that table, DQ. It says one of the ways, well, it doesn't say it on, where is it? Yeah, it says right there on the first table, one of the heat sinks is catalyst, but as you can see, it's a minor heat sink, so it probably is negligible. So that's why, another reason why I didn't include it, but even if I did have, I didn't have information to really calculate any heat removal from the catalyst. The only way I calculated the heat removal, the only variables I used to calculate the heat removal was the feed, the new feed, the heat transfer that would be caused from the hot fluid to the new feed, and the reactor walls, which I just used like thermal conductivities of our material of construction in cross-sectional areas. Yeah, last one, just real quick. We're way over time, but and I'm aware of that. But your safety, were you just worried about the temperature, or what would that do to your pressure? Our pressure would definitely increase as well. We would have a pressure excursion as well if we didn't, with the temperature excursion, I'd assume so, at least, because if you have a increase in temperature, you're going to have more vapor, and that vapor is going to expand and cause a higher pressure. But I guess that's why you have your venting systems, your relief valves and stuff like that. So other than that, I don't know any way to mitigate that other than the relief system. Yeah, and trying to prevent the runaway. So. Yeah. All right. Yeah, let's thank our speakers. Good job, guys. Thank you.
Thank you.
All right, with that, we're going to pass the baton on to the last one we've got for today. So, Rhett?
Yes, sir.
So as a calibration, just for a second and everything, I mean, you know, everyone's kind of seen, you know, groups of 3 and all in this section. I did have a group of 2 and everything. Rhett, you know, had to tackle this, you know, by himself and all, you know, work some collaboratively, you know, on the kinetics and you know, Thermo and everything, but just kind of to calibrate the grading and all the designing of the process and the optimization and everything, you know, worked as an individual. So,
All right, can everyone see everything and hear me
yep.
fine? All right. Well, thank you all for coming out today. Come and watch. My name's Rhett Furman, and this is my project. So just a brief overview. The goal of the project was to design a catalytic hydrocracker unit that processed 50,000 barrels per day of VGO. This is my current topology I was using. I had my feed going into a reactor, the product from that reactor going to a flash drum. The top of that flash drum was my hydrogen that I was recycling, and the bottom of it was my products that went to a tower. That off the top of that tower, I separated my liquid petroleum gases, and the bottom of that tower went to another tower, which separated my unconverted VGO. And then the distillate of that tower went to another tower, which separated my naphtha. And the bottoms from that tower went to another tower that separated my kerosene and my diesel. So this topology gave me an MPV of around 157 million. I had different topologies. My topology before this was around negative 500 million. So I found, and it just had a different separation scheme. So I found this topology to be very useful. So this is just a map of what I'm going to be talking about. I'm just going to be first going into my pricing and costing and my optimizations. Then I'll be talking about my thermodynamics. After that, I'll be talking about my kinetics. And then I'll go into my component justification and then some safety features. So this is just some of my MPV expenses broken down. So as you can see, my reactor was one of my biggest expenses. It was about 82% of these expenses. And the next highest was my utilities, which was about 12. 2 things that are in the MPV that aren't in here, since they're such a higher magnitude than everything else, are my revenue and my raw material costs. My revenue was about 4.6 billion, where my raw material costs was about negative 3.9 billion. So next I'm going to be talking about my reactor. So my reactor, I optimized it, its MPV versus the reactor residence time. And I got my most optimal at 806 degrees Fahrenheit and about 0.66 resident time. So I used a 50,000 cubic feet reactor. And it operated at a pressure of 2,263 PSI. And from my initial reactor to this one, it increased my MPV by about 162 million. And the overall MPV of this reactor cost me about 349 million. So next I'm going to talk about my first distillation column. The distillation column, I optimized its feed tray location versus this MPV. The MPV of this tower included all the reboilers, the surge tanks, the pumps, and all the utilities that go with all that, including the tower's cost and the tray cost. And for all of that, the MPV of this tower is optimal, which was found at the feed tray being on the 5th, and it being at 16 trays was about 5.97 million. And from the initial tower that I had in there, the increase of my MPV to this tower was about 1.7 million. So tower 2 was actually my most expensive tower. I think this was mainly due to my reboiler having to be priced as a fired heater. And so the cost of that heater and the utility costs for it were significantly higher. And again, I optimized this one as the feed load by optimizing the feed tray location and the number of trays. Again, in this MPV, all the utilities and all the various accompanying vessels and other pieces of equipment that go with the tower are calculated into it. And the MPV for this tower was about 22.3 million. And from the initial tower I had in its place to this tower, the NPV increased by around 15.4 million. So for my second tower, I also optimized it by pressure. So I just changed the pressure and saw how the NPV changed. And I got around a little bit less than 2 PSIA as my optimal pressure. And from the initial pressure that it was coming in at, it increased my NPV by around 9.1 million. So for tower 3, I did the same thing as my other towers and optimized the feed tray location and the number of trays. And I found my most optimal to be at the feed tray at 11 and having it 25 trays. And again, NPV included the reboiler, their condenser, and their duties, and the surge tank, and all the other accompanying equipment. And the NPV for this tower was around 5.8 million. And from the initial tower that I had in its place, it only increased it by around $249,000. So this was the lowest increase I had after optimizing any of my towers. And finally, my last tower, I did the same thing as all my other towers. I found the optimal to be at 9 trays with the feed tray location on the 4th tray. The MPV was about $8.7 million for this tower. From the initial tower I had, this increased the MPV by $3.1 million. So next I'm going to talk about my commodity pricing. So for my propane, diesel, kerosene, and my residual oil, I priced them using EIA.gov, and I did a 5-year pricing from January 2015 to January 2020. And for my residual oil, I got about 14 cents a pound. For my liquid petroleum gas, I got about 16 cents a pound. For my diesel, I got about 42 cents a pound. And for my kerosene, I got about 26 cents a pound. So for my VGO, I also priced it at EIA.gov, but their more recent data for VGO had a lot of missing data points in it. So I decided to do a 10-year average from January 2000 to January 2010. And this gave me an average price of about 19 cents per pound for VGO. And then for naphtha, since EIA.gov didn't have it, I got it from Trading Economics. And I did a 5-year average on that too. And I got about 25 cents a pound from that. And then for my hydrogen, I got from the refinerlink.com and calculated it to be about 42 cents a pound for my hydrogen. So next up, I'm going to talk about my thermodynamics. So for my thermodynamics, I had experimental data of the predicted vaporization versus and over various temperatures. So I just put it into a flash drum using different, I put my VGO feed into a flash drum using different thermodynamics. And even though VTPR ended up being the closest to the experimental, it was unusable in KinCad due to extremely long computational times and it just not really working well with the kinetics and all. So I ended up going with Ping Robinson, which wasn't too far off from VTPR, but it simplified my simulation greatly. So next up, I'm just going to be talking about my feed and my cut fractions. So these are the components that I use for my VGO, that I use to simulate my VGO feed. And then below that, I have my different cut fraction cutoff points. And my feed is, the components used for my feed are sorted by boiling point. Next up, this is how I had my my feedstock composition. So I found a source that said that aromatics were about 27% and the non-aromatics was about 73%. So this is how I fed my VGO feed, with it being about 27% weight percentage aromatics and 73% non-aromatics. And these are the components that I use to simulate my product. They're, again, sorted by boiling point, and on side of them, you can see what cut fraction they belong to. So this is the reaction, the kinetic lump reaction model I used. As you can see, I have VGO that can break down into either kerosene, diesel, or liquid petroleum gas, and then the diesel and kerosene can then break down to the naphtha, and then the naphtha then go further break down into the liquid petroleum gas. And on the left-hand side, these were the kinetic parameters that the source gave as an initial, that I used as an initial starting point to try to align my kinetics. These are just my reaction pathways that I use to simulate the reactions in the reactor. The first three are my non-aromatics, and then my last network was my aromatic network. And then this is my my matching of my kinetics. So I matched it at different temperatures and then used a linearized Arrhenius equation to get one set of kinetic parameters that I could use at multiple temperatures that would match pretty decently. And these are the results I got from that. This is it at 788 degrees. This is it at 806. And this is it at 824. Next up, I'm going to talk about how I validated my minimum components I needed to simulate this. So I just put all the components for, I slowly added the components for one cut fraction into a distillation column with a high fractional recovery of about 99.9% of that cut. And I saw how the duties change in the reboiler and the condenser. And so for my feed, I found it to be about 3 or 4 needed, and I ended up going with 4. For diesel, I did the same thing, and I found it 3 needed, but I ended up just going with 4 too. For kerosene, again, I chose 4 as my minimum number I needed. For naphtha, again, I chose 4. And for gas, again, I chose 4. So next up, I'm just going to talk about some safety things. So one of the biggest safety concerns is a runaway reaction and overpressurization. So to counteract this, inside the reactor, I would have multiple layers of multiple thermocouples. And if these thermocouples would both be reading the rate of rise and have a higher temperature limit. And if two of these thermocouplers at any one of these layers would both say that it's exceeding the max temperature or exceeding the rate of rise, then it would open a on-off valve that would drain all the components that are in the reactor to flares. Another thing is for pressure, it would also be reading the pressure, and if the pressure started to go too high, it would initially open a smaller valve to try to release a little bit of stuff so you don't have to completely shut down the unit. And if it's continued to have a pressure issue, it would then open the bigger valve and drain the vessel completely again. My primary way to stop the runaway reactions would be a hydrogen quench, but I did not have enough time to calculate the point at which the runaway reaction would happen, and so I was not able to calculate that higher temperature limit that those thermocouples would need to be reading. Other than that, any questions?
So there's a question about liquid contents or gas contents to the flare.
Yeah, I don't know too much about that. I just know that at Marathon Petroleum and the Garyville refinery, this is how they have their hydrocracker unit running throughout the plug flow and throughout the PFR reactor. they have just after a certain distance, they'll have a group of thermocouples, and I just know that if 2 or more of them say that it's approaching a dangerous zone, if they think the reaction's running away, then it just opens 2 really large valves that just send everything in the reactor straight to the flare. I think it sends everything from what I remember.
You had a 2 psi tower. I mean, did you cost or size some kind of vacuum pump? Or?
I did. In that MPV, it did account for the cost of a vacuum pump, and it was still cheaper due to the using a lower temperature steam to go and make it a vacuum distillation column.
Yeah. Okay. On the Napa, you had that large drop and everything. Did you include that in the average?
I'm sorry?
On the pricing of the NAPTA?
Oh, yes, sir. I had everything from that 5-year. I didn't exclude anything. So it included the large drop.
Do you think that that's where we're going to be? Or
I know it's probably lower due to the whole COVID-19 situation. But I guess I could have took a 10-year average for that one too to get a more accurate representation.
Or price it with and without, just to see how much that's impacting your pricing and stuff. Go back to the reactor optimization. So not much difference in temperature. It for your 0.6 or 0.7 or whatever that peak is. Is that what you would expect? Is that did you see that theoretically with the literature values you got?
I would have expected that the higher temperatures would have had a bigger increase in net present value, but I also had a really high pressure. I wasn't able to optimize the pressure because I didn't have time to. So I feel like if I was having a more optimal pressure, it would have showed a bigger gap in between them.
Yeah, one question, why was your raw material cost negative?
I was just saying negative 3.9 as in it cost me 3.9 billion.
Yeah. You were purchasing it, right?
Yes, sir.
I mean, is what, yeah. Were you concerned about low temperature embrittlement?
I was, but I didn't have time to look into it. I know the reaction is exothermic, so it wasn't as big of a worry for me as the runaway reaction, but I do know it is a issue, but I wasn't able to have the time to go and look into it.
Okay, I think that wraps up at least the questions I'm seeing and everything. So let's go ahead and thank our speaker. All right. All right, guys, that wraps up our, 3 designs that we had, this before the break and the 3 that we've had now. I think the advisory board, we're going to be shifting on and moving to a new Zoom meeting. Typically, I think, the classes we've gotten together had a class picture and everything, and we're not going to be able to do that, unfortunately. I think most of them get together and go out to a restaurant. Unfortunately, we're not able to do that as well. So, hope you guys, maybe the class ought to put together a Zoom and kind of hang out for a while and talk and everything. But I appreciate all the audience, coming in and listening to this. We're proud of everything that, our students have accomplished, and, pleased to be able to present that. Thank you everyone for attending. Thanks, guys.